Hello. So now we are going back to the example and we are going to apply. We will see an example of how the R squared and the standard error of the regression measures are used. So in the test score and student teacher ratio example, we obtained these estimates. So test score is approximately like 700 minus 2.28 student teacher ratio. And the performance of this model, this regression model, is measured by R squared of 0.05, which is 5%, and standard error of the regression being 18.6. Then first, R squared is 0.05, so is it small? It's only 5%, so it means that student-teacher ratio explains only 5% of the test score. Too small? How can we evaluate that? I'm going to talk about that in the next slide. And the standard error of the regression is 18.6. 18.6. But how can we compare this standard error to this or this? Like, we are going to, I will show you how to compare those, how to use the standard error when you judge the coefficient. Okay, first, the student-teacher ratio explains only 5.1% of the variation in test score according to the R squared measure. Does it mean that student-teacher ratio is not important? Usually not. So think about this. Think about how the test scores are determined. If you think about, so without any background knowledge, just list some important factors you came to your mind. Like, for example, like say the kid's intelligence, or the parent's income, parent's education, or teacher quality, or say school facility, or whatever, or what else, like test difficulty, or many things. There are a lot of things. So among those, student-teacher ratio explained 5%. I think it's significant. So it's not, you cannot look down on it. So it's still, without including all the other variables, student-teacher ratio alone explained 1/20 of the test score. I think it's good. You cannot expect more than that from one variable. Okay, so that's how you interpret the R squared. By the way, it's just my personal opinion. I'm not an expert in education, so like education researchers may think and differently. So, but let's just I'm giving you an example how to make a judgment based on the R squared. And standard error of the regression is 18.6, and we can compare this to the coefficient 2.28. 2.28, is it large or small? Of course, we cannot tell. It's subjective whether it is large or small. But from these numbers, like, I don't know what this test is. I don't know whether how good 700 points is and how bad 600 point is. So I have no idea what that means. But you may put those this number to. So suppose that when you increase the student-teacher ratio by 1, then test score drops by 2. Then what is 2? 2, I have no idea. Then you may use the student-teacher standard error. So if you use your calculator, you can find that the coefficient is approximately 0.12 standard error. Standard error of the regression. So actually, standard error of the regression. So it's a 1.2 times 18.6 is 2.28. So this is, so effect of one student-teacher ratio increase is 0.12 standard error. Then how can we tell? Imagine the normal distribution, the standard normal distribution. So we assume that normal distribution, we assume that the errors are normally distributed, which is kind of standard. And then if you assume the normal distribution, one standard error is the difference between the median, the average, the mean, and top 15%, right? So now you can put this in the perspective. Think about there are 100 school districts, and you can rank them by their test scores, and think about their median, and think about top 15%. So the rank 15, and to increase the median school district to the top 15 level, you need about say 8. You need to lower the student-teacher ratio by 8, because one student-teacher ratio decrease by 1 only changes 0.12. So approximately, if you change 8, then it will be 1. So one standard error is approximately the difference between median and top 15%. So median and top 15% is this is much easier to understand and put the numbers in some context, right? So this is another example how the standard error is used, and especially when you measure the size of the coefficients and how significant that is. Okay, that's how we use the measure of fit. And the next chapter, next section, is about assumptions. So we just started with an example, and then we defined regression equation, like what is regression line, and some names, and then I introduced the least squares method, the idea of minimizing the sum of squared errors. That's how we obtained the OLS estimator. And then I hope I could show you how to program that on Stata, but I couldn't do that. And after that, we learned how to measure the fit, the goodness of fit of those models, and that's R squared and standard error. So what's missing here is we did not discuss anything about the required assumptions. Of course, there must be required assumptions for inference, for more formal conclusions, and you need to check if your data are likely to satisfy those assumptions or not. We are going to do that in the next video, and this and the next video. So let me introduce a little bit. So we it's a estimating the regression line is drawing a straight line on the scatter plot. So it's easy, but so think about this. Drawing a line is always possible. So no matter what shape you got, so choose any two random variables, choose two variables, whatever you want, and make a scatter plot, and then you can see some kind of pattern or not. Then you may draw the line as much as you want. However, that doesn't mean they have a true relationship. So, and in our example, for example, I explained as if student-teacher ratio affects test scores. It could be the other way, or there may be no relationship. Just they seem moving together. It does not imply the cause and effect relationship. I'm going to show you an interesting, very strange example where the OLS does not imply causal inference, causal relationship. So, and we are going to study that now. And the second, and after studying the assumptions, we are going to study the sampling distribution of the OLS estimator. OLS estimator has its own sampling distribution, and after deriving the sampling distribution, you can vigorously argue why this estimator is good. So that's a little more theoretical, statistical part, and these two topics are in order. So, and let's think about the causal effect first. The causal relationship is, you know what it is. So when you say X causes Y, then in the experiment setting, when you change X a little bit, Y has to change according to the change in X. So when X changes and X varies, Y should vary systematically following the change in X. Ideally, what we want to do here is, ideally, if possible, we would like to assign the student-teacher ratio by randomization. So randomly assign, suppose, say, Niskayuna School District has 25 student-teacher ratio, and Albany School District has, say, 15, Schenectady has 10, Guilderland has, like, say, 15. So if you could randomly assign those variable, then it's sure that you are going to get the cause and effect relationship. However, in our setup, we do not have those experiments. That's not possible and maybe too expensive. So without having actual random assignment, we would like to check if the data satisfy our assumptions. That's why we are thinking about the cause and effect, other assumptions required for cause and effect interpretation. So, and I have an interesting example. Suppose that Y, you would like to predict COVID cases in the United States in 2020, and say X is the stock market index in the United States, like S&P 500 index. So as you know, in 2020, these two variables both increased drastically, right? So increase like this. So if you draw the graph between X and Y, both will move like this. They will make a very strong positive relationship on the scatter plot. So when you make a scatter plot, you will see a strong positive relationship between them. So you may draw a straight line going through them, right? So, by the way, I did not do this. If you're interested, it would be great, but I'm sure that you are going to get a very positive coefficient. But however, even if you get a positive beta slope, it does not imply stock market increase caused COVID. Obvious, right? So it does, or it, of course, then you cannot say COVID could be slowed down by suppressing the stock market. Stupid statement. This kind of course, in this example, this statement is too obviously wrong. So you know what's the problem. But there are other examples where people cannot tell the difference, making too stronger conclusions using cause and effect terms. So in this case, I will explain this relationship in this way. So stock market, the COVID cases impact government decision, government spending. So government spending impact stock market. So there is another hidden variable, say government spending, government policy, which is affected by Y, and then government affects the stock market. That is, the hidden variable is called confounding variable. Confounding variable is the most common reason why you cannot draw the causal inference, causal conclusion. So you have to make sure there is no confounding variable, no confounder, or we call that like unconfounded, something like that. So it's very intuitive, and I am going to introduce those assumptions in the next video. Thank you for watching.